All right, welcome to episode 19, and this will be a fairly short and specific episode in which we are going to finish supporting the Commodore 16 keyboard, that is the input device for the 6809 system. And there's basically three things that we need to do. We're going to construct a module for the keyboard controller that will plug into our passive backplane, so that way the keyboard controller won't be on breadboards, it'll be a permanent part of the computer. We will add software support to fully support the computer in the ROM monitor program and essentially make it a first-class input device for the ROM monitor. And then finally, the Commodore 16 keyboard wasn't really designed to be placed directly on a flat surface, so I'm going to design and print some supports for the keyboard to make it sit a little bit more nicely on my bench. All right, let's get started. All right, so here is the schematic for the keyboard controller that you may remember from episode 18. And I have constructed this circuit on this proto board. This is the same type of proto board that I've used for the other modules of the system. So we have here an 89C52 microcontroller. That's just what I happen to be using for the microcontroller for the moment. This is the FIFO memory. This is the buffer chip that provides access to the status signals from the FIFO memory so that the host system can determine when there are key presses available. And this is the 74HCT138 address decoder that essentially controls accesses to the buffer and the FIFO. All right, so when you construct a circuit on a proto board from a schematic, there is always the question of does the wiring on the proto board actually correspond correctly to the circuit described by the schematic. And I tested this pretty extensively using the continuity mode on my multimeter to verify that all of the connections were made correctly, and it seemed to be fine. Of course, when I plugged this in for the first time, it didn't work. And what I found was initially none of the column outputs in the keyboard matrix scanning were actually toggling. There were basically no voltage changes on the pins that were assigned to generate the column outputs. And so it seemed like none of the code was actually running. Eventually, what I remembered is that the reset pin on the 8051 family is active high and not active low. I had connected the reset input of the microcontroller to the active low reset of the reset chip rather than the active high reset. So basically the problem was that the microcontroller was being held and reset indefinitely. Once I connected the correct active high reset pin on the backplane into the reset input of the microcontroller, everything worked perfectly. So this module does work. I have added this header that exposes the serial output of the microcontroller that I can connect to the SparkFun serial LCD to get debugging information, basically scan codes, presses and releases as keys are pressed and released. So yeah, so basically this works fine. One thing that occurred to me as I was working on this keyboard controller module is that in general, the approach that I've taken, having a passive backplane and building the different components of the system on these cards, that has worked out extremely well. I have really been very happy with the way this has allowed me to make incremental progress, where I can prototype one module of the system on a breadboard, and then once it's fully tested and debugged, build it in a permanent form on a proto board that can then be plugged into the backplane. That's worked out really, really well, and I would highly recommend using that approach for anybody who is embarking on a similar project. All right, so before I work on the improved software support in the monitor program, I think I am actually going to tackle the sort of physical stability of the keyboard. And the issue is that underneath this Commodore 16 keyboard, there is this bundle of wires that comes out that basically feeds into the switch matrix. And that bundle of wires essentially prevents it from being stable on a flat surface. So the keyboard is mounted in this plastic frame that has these two sort of flanges front and back that have screw holes in them. And so what I'm planning to do is 3D print a sort of a support, two supports that I can screw into this back flange to prop up the rear of the keyboard. That will make it clear of the wire bundle and also will mount the keys at more or less the correct angle for typing as well. So that should make it just sort of a better typing experience. All right, so here's what I came up with for a 3D printed mount to hold up the back of the keyboard. It's in two parts. So the top part is this bracket, and basically the rear flange of the keyboard frame will sit in this slot, and then I will put an M3 screw through the top flange into this screw hole, and then underneath there is a recess for an M3 nut to basically hold the screw securely so it's securely attached to the keyboard frame. And then that bracket sits on these legs, and they are angled such that it will essentially hold the keyboard at an appropriate angle. And I did this in two parts because if I tried to print this as one part, as one single assembly, there would be some weird angles and overhangs, and I'm not sure I would get adequate print quality. So it's easy enough to just use epoxy to glue the bracket onto the leg assembly. So I think that is what I am going to do. All right, let's see if that works. All right, so here are the two keyboard mounts that I printed. So here is the top part is the bracket, and that is epoxied to legs here. It all turned out okay. There's the pocket for the M3 nut. I had to do a little cleanup with an X-Acto knife, but I got reasonable print quality. I've had good luck using two-part epoxy to glue 3D printed parts together, so that seems reasonably sturdy. And basically, these will sit back here and hold up the back of the keyboard. And basically all I need to do now is screw them in place. So let's see if that works. Okay, I have the mounts screwed in place with some M3 machine screws, and this is much more stable. So yeah, feels quite good. I think the frame is perhaps not entirely straight because there's a slight amount of give in this corner, but overall it's quite stable, much better than it was, and it's not putting any mechanical stress on the location where the wire bundle is soldered onto the keyboard PCB, and of course you don't want to put mechanical stress there because that might break some connections. So yeah, I would say this is a win. That definitely works. Okay, time to write some code. Okay, so now we are ready to work on the software support for the keyboard, and essentially it's going to be somewhat straightforward. We just need, in this mon-read command subroutine, which reads a line of input from the user for processing by the monitor program, we need to change this call to the ACIA receive function, which waits for a byte of data to arrive from the serial port. We need to change that with a call to a subroutine which will check both the serial port and the keyboard to see if a byte of data is available, and essentially return the byte of data that is available from either device, whichever one is found first. So what the ACIA receive function actually does is pretty simple. It just polls a status port until a bit indicating that a byte of data is available is set, and then once that status check loop completes, we actually read the byte of data from the data port. So basically what I'm planning to do is add an additional function, ACIA poll, which just checks to see if a byte of data is available, but returns immediately in either case. And so we'll have that function and a new function that polls the keyboard, and then a higher level function which repeatedly calls the ACIA poll and the keyboard poll functions until a byte of data is available. So that's the basic plan. All right, let's think about how we're going to support keyboard input. And the main thing we need to think about is how scan codes work. And basically the idea is that as keys are pressed and released, the microcontroller in the keyboard controller will create a scan code and put it in the FIFO memory so it can be read by the host system. So the high bit of scan codes are unused, and then the next bit, which is bit 6, that is going to be the press or release indication. So basically, if that bit is 1, it means that it's press event. Otherwise, if it's 0, it's a release event. And then in the next 3 bits, we will encode the column number, and those correspond exactly to the columns of the keyboard matrix. There are 8 columns, so that requires 3 bits of information to encode in the scan code, and then the low 3 bits of the scan code are the row corresponding to the row in the keyboard matrix. And again, there are 8 rows requiring 3 bits to encode. And so basically the idea is that the monitor program will need to read these scan codes, and each one indicates a particular key that's being pressed or released. And for the most part, we only care about press events. We're going to generate a character code each time a key is pressed, but there are two exceptions of keys where it is significant when a key is released, which are the modifier keys, specifically Shift and Control. And the idea there is, depending on whether the modifier key is currently pressed, we may want to generate a different key code. So for example, if this 5 key is pressed, if Shift is not currently pressed, then it just generates a 5. But if Shift is currently pressed, then we want to generate the percent character. So essentially our code that processes keyboard scan codes needs to keep track of whether or not these modifier keys are pressed, and if so, generate the appropriate variant character code as each key is pressed. Okay, so let's think about how to do this in software. All right, so the primary problem that we need to tackle in creating the keyboard routines is to map keyboard scan codes into corresponding character codes. And to make that a little bit easier, I've created this text file, translate.txt, and essentially it encodes for each column and row in the keyboard matrix what ASCII code should be generated for the unshifted and shifted cases for each key. So for example, here is column 0, row 1, row 2, row 3. So for example, column 0, row 0, that is the 1 key. So if Shift is not pressed, we generate the digit 1, or the ASCII code for the digit 1. If Shift is pressed, then we generate the ASCII code for the exclamation point. So you will notice that in some cases I've indicated a special character code, and those are cases where I don't really have a good ASCII code in mind yet that should be generated when that key is pressed. So for example, if you press the down key, right now I don't really know exactly what ASCII code I want to generate for that. So it's just sort of left unspecified for now. Okay, so what we do with the information in this translate.txt file is run it through a Ruby script called build keyboard table, and it basically just reads the textual data in the translate.txt file and generates arrays that we can compile into the firmware for the monitor program that essentially allow us to look up by scan code the corresponding ASCII code for the key that generates the corresponding scan code. And I have indicated ASCII codes for a couple of the special keys. So space is ASCII code 32. When return is pressed, we're just going to generate a new line, which is ASCII code 10. So if you run this Ruby script and feed it the translate.txt as input, it basically just spits out these assembly language arrays that we can use to look up ASCII codes by scan code, both for the unshifted and shifted case. And we'll compile this directly into the monitor program in order to do the translation from scan code to ASCII code. Okay, so here are the changes to the monitor program. There are 3 new subroutines. The first of these is ACIA poll, so that polls the serial port to see if a byte is available. It's quite similar to the ACIA receive function that we saw earlier. The only difference is it doesn't poll in a loop, it just checks the status once to see if a byte is available. If a byte is not available, then a 0 is left in the B register. That indicates that no byte is available. If a byte is available, it's read into register A, and we load a 1 into register B, and that indicates that a byte was read successfully from the serial port. The second function is kbd_poll. So this polls the keyboard to see if a byte of data is available. And it's considerably more complicated than ACIA poll because key events include both presses and releases. Only presses will directly generate a character code. However, we do need to keep track of releases because for modifier keys, specifically Shift and Control, we need to know whether they are pressed or released because that changes the behavior of other keys. So roughly what is going on here is we're checking the FIFO status. If the FIFO does not have any data, then we're just done and we set the B register to 0, and that indicates that there's no data available. Otherwise, we read the scan code. We call this keyboard check mod keys function, which looks to see if Shift or Control was pressed or released and modifies a couple of variables accordingly to indicate whether Shift is currently down or Control is currently down. And then we look at the scan code. If it is not a press event, then it's a release event that we sort of don't care about, so we loop and check the FIFO again to see if a press is available. Otherwise, if we know that we definitely have a press, then we look at these two arrays, key code not shifted and key code shifted, to translate the scan code into a corresponding character code, and then we put that in the A register, and that is the character code. So the calling conventions are the same as the ACIA poll function. The character code, if there is one, is returned in the A register, and the B register is either 0 if no character is available, or 1 if a character is available. All right, now that you know that we have these two new functions, ACIA poll and KBD poll, that allows us to define this mon_receive function, and it does pretty much what you would think it would do. It polls the serial port to see if a character is available. If so, returns it. Otherwise, polls the keyboard to see if a character code is available. If so, returns it. And if neither of those is true, it loops and does the same thing again. So this essentially will block until a key is available, a character code is available, either from the serial port or the keyboard. The last piece of the puzzle is the mon_read command function, and all we did is change the original hard-coded call to ACIA receive into a call to our new mon_receive function. And so that essentially gives mon_read command the capability of reading a character code either from the serial port or the keyboard, whichever is available. All right, so here is our setup. So I have the PC keyboard here. That will drive the terminal program directly. Here's the Commodore 16 keyboard. And of course, if we type things here, it should also be registered by the monitor program. All right, I am going to use Minicom to connect to the 6809 system. All right, so let's give it a reset. Okay, that looks good. All right, so as always, I should be able to type things from the monitor program. Actually, let's go to hex 9000, which is the beginning of the ROM code, and let's read 16 bytes. Okay, so there's our 16 bytes of data from the ROM, so that works. I should be able to do essentially the same thing from the Commodore 16 keyboard here. All right, so A9000, as you can see, those characters are registering on the terminal, so that means they are being received by the monitor program. One issue that you'll notice here is that when we hit return, it only generates a new line, not a carriage return, and so that's why the cursor doesn't go all the way back to the beginning of the line. It's a minor annoyance. We'll have to find a way to fix that at some point. All right, so now let's read 16 bytes, and there we go. So the keyboard does indeed seem to be working really well. There's some small issues to deal with, but basically I would count this as a success. Okay, so the keyboard is now fully working and integrated into the 6809 system, so that's great. There are some minor tasks that remain. We need to think more about the encoding of some of the special keys on the keyboard, like the arrow keys. We should support the control modifier, so if you hit control and a letter, it sends the appropriate control code. There are still some things to think about with regards to line termination. These are all pretty minor issues that I don't think will be too hard to deal with. What's more important is to think about what is the next big project for the 6809 system, and what I am planning to do is work on some kind of graphics support. There are two options I'm considering. One is to use the TMS9918A graphics chip, video display processor. That's definitely an option. It's probably the best vintage part for generating graphics, although it has some problematic aspects. The other option I'm considering is to try to use an FPGA and essentially develop our own video processor. The big advantage there would be the ability to generate video output for something more modern than composite video. So I'm not sure which way I'm going to go. That'll be something to think about. Okay, so thanks for tuning in, and I will see you in the next episode.